Hello class, so this week we're going to be starting in a new direction and looking at different statistical techniques that basically measure the degree of a relationship between two variables. This is kind of a different direction from what we've been looking at the last couple of weeks, which looks at differences between groups. There's really two things we're going to cover in this, and usually the type of stuff we're going to cover this week and the week after we come back from break is more generally what you'd be more likely to do in criminal justice research, because we don't use very many experimental designs, so we don't often have control groups, and we don't often do group comparisons unless we're doing some kind of treatment program and comparing groups that are in that. But the first thing I want to talk about today, we're going to be looking at bivariate correlations in this unit, and the week we come back we'll be looking at what's called bivariate regressions. And both of these are techniques to essentially measure the relationship between two variables. We'll probably won't actually do any calculations with the regression because it gets pretty involved, but we will do it with the correlations here. But okay, objectives for this week: I want you guys to understand the purpose of correlations, what is a correlation, basically how to interpret them. We also want to be able to interpret these, or at least understand them visually, so we'll look at what's called scatter plots. And then we'll also be able to compute, actually scratch this, we're not going to be computing the covariance, but we are going to be computing correlation coefficients this week. And finally, we're going to talk about some various weaknesses, or some various problems that can come up in correlations. And we'll briefly discuss that there's different types of correlations that we would use, but we're not going to spend much time on that. But the first thing I wanted to focus on today was kind of do a recap of some of the techniques we've done in this class, and this isn't everything we've done. But what I really want to do here is try to explain, okay, when you're looking at inferential statistics, we already talked about there's descriptive and inferential statistics. But what we've been covering for the last couple of weeks has all been under that inferential branch of statistics. And one thing I want to talk about is, okay, depending on what type of research you're doing and depending on what you're trying to do, what type of statistic should you use to answer your research question, basically. And I essentially created this flow chart that you guys can come back and refer to that might help you with this. But the first thing you have to consider is the type of data you have. And usually what we're talking about here is, do you have continuous data or do you have categorical data? If you guys remember back to the first couple of weeks, continuous data would be stuff that's either interval or ratio, like age, number of crimes a person's committed, some kind of value on a scale like a self-control scale. Those would all be continuous. But on the other hand, we had categorical, which would be stuff like gender, a person's religious affiliation, things like that. So that's the first thing you have to ask whenever you're doing statistics and you want to learn anything. Am I dealing with continuous or am I dealing with categorical variables? And if you're dealing with categorical variables, one of the things you can do that we've learned in this class, the only one thing that we've, there's other tests you could run, but the only one we've learned in this class was the chi-square. And if you guys recall from last week, the chi-square is basically to see if there's a relationship between two categorical variables. But on the other hand, okay, if we have continuous variables, which is what we have most of the time, then you have to ask yourself, okay, what type of question am I asking here? What type of research question? And that really is asking, are you looking at relationships between variables, or are you looking at differences between groups? So relationship between variables. Simple one there would be, okay, is age related to basically crime? Do people commit more crimes at a certain age? That type of stuff. That would be a relationship. Looking at a relationship there. Is there a relationship between age and crime? On the other hand, if we're looking at differences, then we'd be looking at stuff, usually we're, again, comparing groups. So we could be, for example, comparing males and females. We could be comparing, again, a treatment and a control group. So our next decision on what we should do is based on that. And if you decide that you're doing some type of relationship study, or study of the relationship between two variables, then you'd be doing what we're starting this week. It's called a correlation or regression. And so we'll see in a bit more detail what that is this week. But again, the stuff we've covered up to now, most of that's been looking at differences. And if you are looking at differences between groups, then obviously you need to consider the numbers of groups. And if it's two groups, then we have the t-test. If it was three or more groups, we have the ANOVA. So that's just a quick review of deciding what statistical technique should I use? This will show up on your guys' final test in this class. Basically giving you guys a scenario of, okay, let's say you're comparing two variables, and you want to look at the relationship between these two variables, and maybe it's a example going back to my age and crime relationship. What statistical technique should you use? And you should probably say either correlation or regression based on this. Again, if the question asked if you were looking at differences between variables, or sorry, differences between different groups, and I give you some kind of scenario related to that, then you'd want to break it down to this, the number of groups, and figure this out. But this is a good thing to remember that. Now, in reality, our flow chart here can be much more extensive than this, because what we've covered in this class is only a small tip of the iceberg of the statistical techniques that are out there. But this is a good start, and if you guys are out reading research journals, most of the stuff you're going to read is related to the things that we've covered in this class, unless they're getting into some fairly high-level things. Alright, but that leads us up to my discussion. This week we're going to be talking about correlation. And as I just said in that last slide, a correlation basically measures the relationship or association between two variables. So a couple examples here: how much a person studies versus their test performance. Okay, that's something that we would normally think there'd be a relationship in, and that we would think that the more a person studies, the higher they should get on a test. That would be essentially a linear relationship there. Cigarettes smoked and lung cancer would be another relationship we could examine. And again, our hypothesis might be that smoking more is related to a higher instance of lung cancer, a higher chance of lung cancer. Salary and happiness is another thing we could look at relationships. So there's tons of different things we could explore with correlations and regressions and exploring relationships. And as I said, based on the type of research we do in criminology and the criminal justice field, most of our stuff is more on this relationship side. Almost any statistical test that we do, any test of a theory, a criminological theory that we do, usually you're going to be using one of these, either correlation or some form of regression to test that. Okay, there's lots of different types of correlation. They basically all try to measure the association between two variables. The one we're going to be looking at in this unit and for this class is the Pearson correlation coefficient. It's probably the one that's used most often. Just a few basics about correlations though. Whenever you calculate a correlation, you're basically going to get a value that ranges from -1 to +1. It can't fall outside of that. And this is how it allows you to interpret it, because the closer to the extremes, the closer it is to -1 or +1, then the stronger the relationship. That's how you would interpret pretty much any correlation. It's going to have that -1 to 1 value, and then the closer it is to one of those sides, the stronger the relationship. And obviously, if you have a negative relationship, you'd end up getting a negative value. And the stronger, or basically if it's closer to -1, then you would have a stronger negative association between variables. And that basically, a negative relationship basically means that as one variable increases, the other variable decreases. Most of the stuff we're looking at under correlation and regression assumes a linear relationship between variables. You want to remember that. It assumes a linear relationship between variables. So a negative relationship, what we'd be assuming is that when one variable increases, the other one decreases. We'll see a visual representation of this here in a minute. Positive relationship basically says as one value increases, the other increases, or as one value decreases, the other decreases. So they're basically traveling in the same direction. And then obviously you could also have no relationship. A no relationship within a correlation would be represented by a 0. And then also the closer you are to 0, the weaker you would say that relationship is. Now here in a little bit I'll give you guys a rule of thumb for interpreting correlations results. But first let's look at some visual representations of correlations, and that's usually one of the first things you'd be doing if you're looking at the relation between two variables. You'd want to get a visual representation, and the tool you'd use to do that is what's called a scatter plot or scatter diagram. And it's basically an figure in which your individual data points from each variable are plotted against each other. Let's go back to that. So y generally, you want to remember this too, y generally represents your dependent variable within a relationship, and x represents the independent variable. So if we went out and we had our values across here for x and up here for y, then each person, again, would have a value for x and y, and we'd find where they intersect on this graph. And that would be our scatter plot. Now, one thing you can figure out by just glancing at a scatter plot, you can generally get a general idea of is there a positive or negative relationship within a study. Now, the following example shows you guys a graph of the relation between health and exercise. And it essentially shows, you can see here, that there's a pretty strong positive relationship. And if we would have actually ran the numbers on this, we'd get a correlation of 0.968. So this is what a very strong positive correlation would look like if you graphed it out. Likewise, if we looked at a negative correlation, it would generally look like this. If we looked at the relation between hunger and food, how much somebody eats, we would generally expect that to have a negative relationship. The more you eat, the lower your hunger level gets, which is what we see represented in this table. And you can see down here, this is a strong negative correlation, and we can see it represented visually here. Now, a few more things, just to represent what no relationship would look like visually, you would essentially get something like this. So this is ice cream eaten and words remembered, no relationship whatsoever. That came out as a 0, basically, on this correlation coefficient. Now, a few other things that you could get by graphing this out that's important. You could determine is the relationship between two variables actually linear, because one thing you can run into what's called a curvilinear relationship, where maybe it starts out linear and then starts doing something like this. And if that's the case, your correlation coefficient, or any type of thing that's based on that assumption that you have a linear relationship, probably won't give you accurate results. So that's another reason. It's basically one of the assumptions of all these tests, is that you have at least a fairly linear relationship. But okay. As I already said before, the Pearson's R is the correlation coefficient we'll be examining in this unit. It's basically a correlation that standardizes the covariance between x and y, and then gives you the value based on that. So you want to remember it's a standardized. It basically takes the values of x and the values of y, standardizes those, and then basically looks at the relationship between them. And it gives you a standardized one because they have to be standardized, because if you're using the original measurement, you might get some pretty funky things. Just real quick, if you were interpreting this, and I will say here, interpreting your correlation coefficients, there's no completely agreed upon rule for what a certain value represents. But in general, for this class, we could consider that either plus or negative 0.30 would be, or below would basically represent a weak relationship. About 0.50 would be a moderate, and about 0.70 would be a moderate strong or a strong relationship. And again, different authors and different statisticians give different interpretations on that, but that's what we'll have for this class. So if you had 0.30 negative, that would be pretty much a weak negative relationship. Obviously, at a positive value would be a weak positive relationship. So you want to remember that. You want to remember how to interpret based on these rules of thumb. Okay, let's get to the actual calculation aspect now. To calculate your Pearson's R, you have to follow the following formula, which looks pretty daunting, but it's not too bad when you actually get all the stuff that you need for it. And on this formula, okay, it probably looks more daunting because we got x and y's mixed in here, but x just represents your independent variable, and y represents your dependent variable, and then n up here represents your sample size. So it's actually not too, there's a lot of steps involved. So it's easy to make a mistake during your calculations, especially if you mess up your order of operations. But if you follow the proper steps, it's pretty easy. We'll do an actual example when we do our major example for this unit. But one other thing I want to talk about, a lot of times you'd see statisticians report what's called the coefficient of determination. And this is basically just the square of R. You're squaring R. So you calculate your correlation, so your correlation coefficient, is r, and then your coefficient of determination, which is sometimes also called r squared. Again, it's just simply squaring r. This is easier, as we said, we just saw a few slides a little while ago. I was talking about interpreting r, and it's kind of wishy-washy. We have this kind of rules of thumb. But this is one reason you see the coefficient of determination used. If you do this, it's actually easier to interpret just by simply squaring r. For example, if we had a correlation of 0.60, and this is a correlation between self-control and self-reported delinquency. What would this tell us about self-reported delinquency? Well, it's a positive correlation. We know that. It's 0.60. Going back to our rule of thumb, that would probably be a moderately strong relationship. But if we square this, what do we get? Well, we get 0.36. And what's good about the coefficient of determination is that you can interpret it based on a percentage. And we could basically represent this as self-control explaining 36% of the variance in self-reported delinquency. So it's a bit more relatable as far as interpretation. We don't need to worry too much about that for this unit, but it'll come back when we talk about regressions. Alright, so let's get into actually hypothesis testing with R, because all we've done so far, I showed you guys the formula to calculate R, but even after you calculate R, you have to basically still do your hypothesis testing to see, is the relationship you find statistically significant? And so our first thing, as always, would be to provide our null and research hypotheses. If we were going through a hypothesis testing, well, first we'd have to calculate R, but then we'd get our null and research hypotheses. Your null would basically be there's no significant relationship between the variables, and that's the key here, no significant relationship. And the alternative hypothesis is there's no statistically significant relationship between the variables. There is a statistically significant relation between the variables. Obviously, this is a two-tailed test. You could also do it one-tailed. For example, if you're predicting a positive relationship between two variables, you might say that here you'd still say no significant relationship, but your alternative would be that there is a significant positive relationship between the two variables. But that's pretty straightforward. The big difference here between what we've seen before is that we're saying there's no statistically significant relationship rather than difference. As usual, we have to calculate our critical values when hypothesis testing. And actually, to do this, we just use the t-distribution. And it's pretty easy to get. We're going to use that same t-table we've used throughout this class. And what we need our alpha level and our degrees of freedom. And you calculate your degrees of freedom when you're looking at correlations by looking at n minus 2. So your sample size minus 2 gives you your degrees of freedom. And obviously, as usual, if the correlation exceeds our critical value in either direction, if we're looking at a two-tailed hypothesis, then we would reject our null hypothesis. It's pretty straightforward, not too much new there. So again, we can have two-tailed or we can have one-tailed. Okay, then our next step would be to actually run our test statistic, which is basically a different type of t test here, because we're using a t-distribution, but it's really simple if you've already calculated r, because all we need is r, our sample size, and then r squared, and we can calculate that really easy, so we'll come back to that. So now let's look at an actual example and pull all this together that I just talked about. So for this example, let's say we wanted to examine the relationship. We wanted to see, is there a relationship between the number of hours a person watches TV in a week and the number of hours they study in a month. So in this example, this would be our IV, this would be our dependent variable. And let's say that we want to set our alpha level at 0.05. And we get the following values. We have 5 people in our study. First person watched roughly an average of 20 hours of TV a week, and they studied 72 hours a month. Next person, 17 and 94. So again, here's each person. This represents the number of hours they watched TV. This is the number of hours they studied. So now we want to basically calculate a correlation, a Pearson's correlation based on these values. Then we want to go through our hypothesis testing steps. So again, first thing we need to do is actually calculate our Pearson's R. and this has got to be the most involved step. So remember, here's our equation up here. It looks pretty daunting, but it's actually not too bad. We only need a few things here. We need to know, if you look at it, we need to know, okay, sum of x, sum of y, so we need to calculate the sums of x and sum of y. We need sum of x squared, so we need to calculate that. Sum of y squared, so we need to calculate that. But everything else we can just plug things in if we get those. So as usual, it'd probably be pretty easy to do this in Excel. So I'll pull this over. So as I said, looking up here, we needed x and y. We already have that, so we need the sum in each of those. Which gives us 67. I already wrote it out down below here, and 454. Now we need x squared. And you guys remember that's pretty easy to calculate in x squared or in Excel. So x squared, we want to do a2 times a2, hit enter. That gives us that for this one. Then if we hit Control C and paste it on down to here, we get that for the entire column. And then once again, we can get the auto sum of that. That gives us the sum of x squared. Let's do the same thing for y squared. So b2 times b2, hit enter, Control C, all the way down, Control V, get the auto sum of that. And then finally, we also need x times y, which we need that for this right here, the sum of x times y. So we can also do that here. And again, we can do that pretty easy in Excel. Our equation here would be equals a2 times b2. Gives us 1,444. Control C, copy it all the way down to do the same thing in each of these columns. So you can see this one's doing A5 and B5. And then get the sum of that. Okay, bam. Now right there we have all the information we need to calculate R in this equation. So let's keep this here where we can see it. And okay, let's actually, I've already kind of done this for us, but if we were to plug everything into our equation here, here's what we get. Okay, we need n. Our n is 5. We had 5 people in our study. Sum of x, 67. Sum of x squared, 454. Oh. And actually, I made a little mistake. Let me go back and change it. And for this, I think what I'm going to do is actually go through and show you guys how to write out these equations in Microsoft Office. That way, it's easier for you guys to show your work in the homework assignments. So let's move this. It's not listening very well. Move this down here. Here. So if you have the newest Office, this is how you would go about doing it. You would go Insert, come over to Equation. That gives you this box here. And then you would put equals. Okay, if you look at our equation down here, n times the sum of xy. So n is 5, and the first thing we would do is put these big brackets to put everything else in, and then 5 in this one, and we times that by the sum of xy, which we have in this column, 5972, minus the sum of x times the sum of y. And the sum of x, if we go over and look over here, was 67. The sum of y was 454. And now, again, the reason we put this big other bracket in here is so that when we hit divide here, it puts it all up here on top. Okay, then we'll come down and click on this little box down here and put the bottom part of our equation. And we need to come up to design here and click on this radical, which will allow us to put in the basically the square root value. So then we click on the box under that, and we start putting in based on our equation again. So with what we have here, let's use brackets again. We have 5, sorry, put 5 there, times the sum of x squared. So 5 times, come over and look at sum of x squared, 1015, minus sum of x, which remember is 67, and then we need, come to the script part here, click on this one, that'll allow us to, actually, if I click here, okay, actually what I need to do here is there's some way I got this to work right. 67, and then script up here, click on this. Okay, so if you highlight the 67, then I'll give you that, make it again squared. Then we should be done with that. But it's not letting us come down. That's why this is annoying to do in Microsoft Word. Okay, if we just come over and make sure to be away from that and click down here. Put our bracket there. Now let's put another bracket going this way and finish out our equation here, which is basically the same thing we just did but with the y side. So 5 times y squared, 41782, parentheses, minus sum of y, 454, squared. And put our final bracket. So that represents our first equation there. Now I'm just going to skip ahead and do all the rest, and so you guys don't have to sit here and watch me do all these, but I'll go through all the steps. Alright, so I went ahead and just went through the order of operation here. You can see plugging all the values in. N is 5, 5972 comes from our sum of xy, sum of xy 5972, minus sum of x 67 times sum of y 454 over the square root of n times the sum of x squared, which was 1015, minus sum of x then squared, so 67 squared, and then kind of the same thing over here, 5, 41792, which is our y squared, minus the sum of y squared, so 454 squared. We calculate that out, doing order of operation, we do this and this up here, giving us 29860 minus 30418 over the square root of, again, do the multiplication first, and we can do that, and then do this and this, and we get 5075 minus 4489, and 208910 minus 20616, sorry. And then if we calculate that out, we get 558 over the square root of 586 times 2794. Go calculate it out further, we get 558 over the square root of 1637284, and then we get 558 over 1279.6, and then finally r equals 0.44. So now that we have that calculated out, we can actually start our hypothesis testing. So we have a correlation value here, and if we were to interpret just that, that would tell us that there's basically a moderately weak relationship between the two variables. But let's go through and do our full hypothesis test. Alright, so moving on, we got our R value, our Pearson's R. So the next thing we want to do is do our hypothesis testing. So sting our hypotheses, we'd basically say null would be that there's no significant relationship between hours of TV watched and hours studied. Where alternative, again, we're doing two-tailed here, would basically be that there is a significant relationship, although we wouldn't be a statistically significant relationship is what we should be saying, really, although we're not going to specify a direction. Critical value, as I reviewed earlier, basically we need a couple things. We need our degrees of freedom, our alpha level, and whether we have a one or two-tailed test. We already know we have a two-tailed test, and alpha level 0.05. Degrees of freedom is n-2, so 5 people in our study minus 2 equals 3. Alpha is 0.05. So if we were to go back and actually go to the same t-test we've used for a bunch of the other tests, I'm not even going to pull it up this time because you guys should be familiar with it. You would, again, look at your degrees of freedom. From there, look over at your alpha level for a two-tailed test, and we would find a critical value of plus or minus 3.182, meaning that if our value does not fall outside of plus or minus 3.182, we're going to reject the null. So next thing we need to do is calculate our test statistic with the following formula. T equals Pearson's R over or times the square root of n-2 divided by 1 minus basically R squared. So if we just, real simple here, we just plug in our values. R equals 0.44. Sorry, there's a typo there. That should not have been negative, so 0.44. And if we square that, we get R squared 0.194. So now we have everything we need to calculate this. So plugging in our values, 0.444 times square root of 5 minus 2, n being 5, over 1 minus R squared, 0.194. Do our order of operation, we get 3 over 0.806, square root of 3.71, 0.44 times 1.93, and then finally t equals 0.85. So now we can say our t equals 0.85, so we can draw our conclusions and say, okay, that our t value of 0.85 did not fall outside of our critical value of plus or minus 3.182. Therefore, we are going to retain our null hypotheses and conclude that the relationship between the two variables is not significant. So even though, again, the correlation coefficients show that there is this weak relationship, it's not statistically significant, meaning it's not something that we would expect to occur outside of chance. And just real quick, part of the reason that might be is because we had such a small sample size. A sample size of 5, whenever you're looking at relation between variables, it's going to be really hard to find a significant relationship. Usually you want a sample of at least 30 or 50 if you're going to be comparing relationship between variables. 5 just really isn't enough, so it's not surprising that we did not find our t value, or critical value basically, sorry, our test value fell within our critical value so that we retained the null here because we had such a small sample size. So remember that. Sample size is pretty key. Obviously another thing we could have done, but it probably wouldn't have made a difference here, is we would have done a one-tailed test instead of a two-tailed test. We might have been more likely to reject the null. So just to recap there, even though you can see that, and also we have some stuff here like a person that watched 6 hours of TV probably studied the less, and then some of the people also that watch a lot study less, but we also probably have a mixed up relationship here. But also just because there's so few people, it was hard to find a statistically significant relationship. Now, if we were to find this significant, we'd probably change our interpretation, and here we'd say that our t value was significant, and then we would go on to interpret the actual r. So we might say r equaled, again, assuming this was significant, 0.44. This represents a moderately weak relationship. So if you do find it significant, you do want to interpret that as well, interpret the actual r. Okay, just a few more things to talk about for this week. These are some other factors to consider that might affect your correlation. We just talked about sample size, Cam, but two other things here. This should be two. Again, I had three, then decided not to have one of them. One of those is if you don't have linear relationships between x and y, then correlation isn't going to work very well because it assumes that. And then also if you have what's called heterogeneous subsamples, this can affect it. So I'll go into each of these individually. Nonlinearity, I already talked about that. But usually what we're talking about here is a curvilinear relationship. It looks something like what we have here, where it starts to curve down after a while. So for a while it's straight and linear, but then it curves. And if you were doing a correlation on that, it wouldn't really be a good picture of the relationship between two variables. And it would really depend on where we looked in this curve as to what our correlation is. Because if we looked here, we'd have a positive correlation. If we looked here, we'd have a negative. So it's not really the proper test. That's one reason you always want to run those scatter plots before you do any of these. Heterogeneous subsamples means that you actually end up having distinct groups within your people in your study that might respond to things differently. So for example, if you're doing height and weight of US adults, well, if you didn't account for gender, we might get a correlation of 0.59, but if we did, you might actually see a stronger correlation for males and a different correlation for females. So that's just something to take into account, but it's not that big of a deal. But the last thing I want to talk about, and if you guys had the research methods class, you probably got this driven into your brains already, but correlation does not mean causation. We often test correlations in a way to try to show causation, but we can never truly say that one variable causes another. So, and that's to say, in this respect, not all results are going to be meaningful. Even if you find a really strong correlation that's statistically significant, it's not always something that's meaningful. For example, something that you'd probably find a pretty strong correlation between would be the amount of ice cream consumed in a city during a given month and the number of deaths due to drowning. Those would probably be strongly correlated, but they're not strongly correlated because eating ice cream causes drowning. They're strongly correlated, but there's also probably some third variable that's affecting both of these, which more than likely would be hot weather. So what we'd be looking at here is basically that's one of the things you have to be careful when you're conducting research, whenever you're doing correlations or regressions, you're looking at relationships, as you need to control for third variables and take those into account in your interpretation. Basically just saying that there's a correlation is fine, but you usually don't want to take that extra step and say that one variable causes another, because there could always be a third variable out there that's really influencing both of those. So, big thing on the test, correlation does not imply causation. Just to give you another example with that, again with ice cream, if you looked at ice cream and aggravated assault, you might get a correlation of 0.2, which shows, again, a weak relationship. But what's probably going on there is that temperature affects both these, and it's a mediating variable between the two. So if you get into some really advanced statistics, which we won't get into in this class, there's actually stuff and models to try to look for these intervening variables. We don't really need to cover this last part, but that's it for this week. As usual, if you guys have any questions, feel free to contact me. Your assignment for this week is basically going to be calculating a correlation and then going through this hypothesis testing with that. And so I showed you guys how to do the equations in Microsoft Office. So when you're doing your homework, I encourage you guys to do that, just so when you make a mistake, or if you do make a mistake, I can pick up where that mistake was, and I'll take off less points if the rest of your equation is fine, except for that mistake. And I know some of you guys already show your work in that manner, but just try to do that, and it'll make grading easier and probably help you guys get better grades, which everyone's doing pretty well in this class, actually. But it would just make things go a little bit smoother if you guys were able to do that. But anyway, you guys have a great week. As I said, the next week that we have class, we're going to have basically going into regression, and then we'll actually be done. So, we're really close now. But everyone have a fantastic week.